Section 7.3, work done by the gravitational force. So we can calculate the work done by specifically the gravitational force if we just take our work equation and plug in our gravitational force, right? So instead of the F, we're going to plug in mg, because that's what our force is here, times the displacement times cosine of the angle between the force and the displacement. So this is really just looking at a specific subset of the previous equation. Not all that new. But we can check a few common cases, right? What about when we have a rising object? So the object is going up into the air. Well, in that case, the displacement is going to be positive. But what direction is the gravitational force acting on? Gravitational force is pulling down on it, right, with the mg force. So what's the angle between the displacement and the force? That's 180 degrees. And so we get a -1 for that cosine. And that tells us that the work done by gravity is negative mgd for a rising object. If instead the object is falling with some velocity, like an apple or a ball falling through the air, well, notice that is now in the same direction as the force of gravity, mgd, or mg. So the angle between the displacement and the force is 0, and we have cosine of 0 is +1, and we can calculate the work done by gravity is now positive mgd. What does this mean? Well, think about if an object is rising in the air, then it is losing kinetic energy, right? So the work done by gravity is it's removing energy, transferring it from the object. As the object starts to fall, it moves faster and faster, it gains kinetic energy. And so now the work done by gravity is actually transferring energy to the object. And that's why the work done is positive versus negative. So the signs here really do matter. All right, now we could also think for a moment, not just of tossing a ball, but what if we're lifting or lowering an object, right? Well, either way, you can imagine we have, like we're weightlifting here. Throughout the motion, we are going to be supporting that bar, right? Keeping it from falling and crushing us. So even when we're raising it and when we're lowering it, we're applying an upward force to the object. So that would be, let's see if I can get a sketch going up here. So if we have, say, an object, the force of gravity is coming down, mg, and we're applying a force to support it, to fight gravity. So that'd be F sub A for the applied force of what we are bringing to the table. So we know that the change in kinetic energy, K final minus K initial, is equal to the net work done. If we have two forces that are acting in the direction of the motion, then the net work will be the work done by the applied force plus the work done by gravity. So this is a handy sub-application again of our overall work kinetic energy theorem. The change in kinetic energy is equal to the work. That's the much better general equation. But for this subcase, we can look at the limiting case that what if the kinetic energies are 0? So if we hold an object and it's not moving, and then we lift it up and it at the top is not moving, well then at the end, as well as at the beginning, the kinetic energy is 0. So the net change in kinetic energy is 0 as well. The net work applied, plus work done by gravity is equal to 0. And so that tells us that the work applied is always going to be negative the work done by gravity, because the force is acting in the opposite direction. So it's going to have the opposite sign of work. In other words, for an applied lifting force, you can find that the work applied is negative mgd cosine of phi. I don't really like this equation, so I don't highly recommend using it because it depends on this angle being between gravity and between the displacement, not the applied force. But I do think it's reasonable that the work applied is negative the work done by gravity. That's a better equation to use. It seems a little safer to me. You can calculate the work done by gravity and know that the work done by the applied force is just going to have the opposite sign. A useful thing, though, is that this equation applies regardless of path. So I talked about a simple example of lifting straight up, right? But I could have also walked for a while with the bar. I could have lowered it further and then lifted it up higher, and it would end up being the same amount of work done by the applied force versus by gravity. Pretty wild. And that's in part because of this specific definition of work that we have for physics. All right, so here's a few examples showing the applied force and the force of gravity, right? And so in every case, whether the object is being moved upward or lowered, so the upward displacement on the top and downward displacement on the bottom, we see that if the forces are in the same direction, that force is doing positive work. If the force is acting opposite the displacement, that force is doing negative work. And so which one's doing positive work will depend on if you're moving up or if you're moving down. Note that the works don't have to be equal. You might be doing more work in applying a force than the work done by gravity. But in that case, the change in kinetic energy will not be zero, right? So we'll only see that the works are equal and cancel if the initial and final kinetic energies are equal. If the works are unequal, you'll need to know the difference between the initial and final kinetic energies in order to solve for the work. So it might tell you that it's at rest to start and then it's going at 2 meters per second. Well, that can tell you the change in kinetic energy, and that will tell you the net work. So there we have it. Let's look at a brief example here. You're a passenger being lowered down in an elevator. Which forces do negative work? Which forces do positive work? So I want you to think for a moment about this, come up with an answer to both questions before you move on. So go ahead and pause now. All right. Well, first off, we need to think about the forces in the elevator, right? So one of our forces is going to be gravity. Can't get away from it. It's always pulling us down. So we have the force of gravity pulling us down. What other forces are acting on you in the elevator? Other force is the elevator cable, the tension that's supporting the entire elevator. Or if you don't want to think of the elevator as the object of interest, you could have talked about the normal force that's supporting you. That would be equally valid, depending on your perspective. So we'll note that one too. So the normal force would be if you're talking about the forces acting on you as a person, passenger. The tension would be if you're talking about the forces acting on the elevator. Now to figure out what forces are doing positive versus negative work, we need to write down our displacement. So it says we're being lowered down. So that tells us our displacement is downward. So the forces doing positive work are the ones that are in the same direction as that displacement. That's going to be gravity is doing positive work. Which forces are doing negative work? It's going to be the ones that are going against the displacement. So either the normal force or the tension as shown. So here it's focused on the elevator cab. So it says tension does negative work. The force of gravity does positive work. In other words, the force of gravity is helping you move down while the tension is supporting the elevator so that you do not move down too quickly, which is a good thing. We were very glad for elevator cables when we were in an elevator. So we'll wrap up the section right there.